Okay, we're back looking at our kurtotic residuals for time, and we're looking at doing some transformations to see if we can fix this kurtosis. And there is some skewness in time, but that's not coming up in the residuals, so I'm not so worried about skewness. Now, right skewness is fairly simple to fix. Usually a square root transform or a log transform will do the trick. So we'll do that now so you can see how to do it if that's the problem with your data. And honestly, right skewness is probably 80% of the problems that you'll see in your data. So under calculator, calc, store result in. Now if you just give minitab a name and it can't find the name in your columns, it will create a new column and call it that name. So let's call it log of time. So what we're doing is we're trying to squish time around to make it more normal. And the functions over here, if you don't have a lot of maths and you don't really understand exactly what a logarithm or a square root is doing, you could play around with your calculator and just have a look at what happens to the numbers when you take the logarithm or the square root. And what's going to happen is it's going to make them all smaller, but it's going to have a bigger effect on the really large numbers than it has on the small numbers. So if that's as far as your maths understanding goes of logarithms, then that's absolutely fine. You can still work with that. Students often ask me, does it matter if I use the base 10 or the natural log? And the answer would be, if you're not sure, try them both. I don't think it's going to make much of a difference in this case. So I'm just going to choose the log to base 10. Usually just in terms of notation, usually if someone's written log without any base in it, it's probably base 10. And if someone's written ln, it'll be the natural log to base e. So I'm just going to put log 10 and time. And hopefully we've got a new column. You can see that I've already done a whole lot of transformations here. It's created a new column here, C19, and this is all the log of the time values. So I'd be interested to see what it has done. So let's have a look at our log 10. And that's quite nice, really. It's pulled in the right-hand side, so it's not so skewed. And we do still have the problem with the kurtosis. We'd probably have to spit out a measure of kurtosis to work out if that was less than it was with just time. So what I did in the video, if you've watched the overview, is I did a whole lot of transformations, and then I looked at the skewness in kurtosis and the histograms for all of them, and then I just picked the best one. And I was interested, because I knew kurtosis was the problem, I really wanted the one that minimised the kurtosis the most in the time, in the hope that that would minimise the kurtosis the most in the residuals, because it's the residuals that I'm really worried about. So here I've got a whole lot of columns where I've done the square root of time, 1 on time, log 10, log base e, and then I did something that can happen. If you're not sure what is the best transformation and you get onto Google, you may turn up some more complicated transformations. So in this case, I came up with this little beauty here using an arctan. So the input, which is the time in this case, minus the mean over the standard deviation by a constant value. And it says here where C is the constant that controls how far the extreme values are brought in towards the mean. It doesn't actually tell you how to work out the best value of C. So you'd have to, if you were doing a serious analysis, you'd probably want to chase up some of these references and see if you could find some more information about this. I just guessed a few values and just had a look at what they did. So I can show you how to put in a more complicated formula into minitab, because it can do quite a lot of stuff. If you're more comfortable in Excel, then I guess you could just do it in Excel, but it really is fairly simple in minitab too. Here are all the arctan transformations I tried with the different C values. So under the calculator menu again, calc. So I'll call this new arctan. Now the expression here, we had our value minus the mean. So that would be a statistics function, so mean, and we want the mean of time in this case, and I only have a very short memory, so let's have a look at the formula again. Input minus the mean over the standard deviation, so divided by the standard deviation of time. Now let's pop this all in brackets, close, just Control X and paste that inside the brackets, Control V. So that means I've got input minus the mean over the standard deviation. Now this is the constant value. If you weren't sure what to do, you could just leave that, well, not put anything in, and that would be a C value of 1 and see what that does. And then if that doesn't work, you could try the next one up and try another number and see how that goes. Or again, if you're serious, chase up some of those references. And then at the front here, let's select it all. Now if we select it all and then tell minitab what to do, it'll probably put that all in brackets again and put the arctan around it. So that's a trig function. If you're not sure what kind of function it is, you may just have to show all of them and have a look through. So arctangent, and it has put it around all of it. Okay. So we've got the new arctan over here. So let's have a look at that. Okay. So this has been quite a severe transformation. We've actually gone skewed in the other direction now. Well, it looks like it's been pulled out a little bit more on the left, and it still hasn't fixed the kurtosis. So I don't know if that very complicated formula was worth all the effort in this case. Now to compare them all, once you've done all your transformations, and it may just be a case of just doing the square root or just doing the log, and then you'll find that that fixes your problems and you don't have to do anything more complicated. But I'm going to have a look at the descriptive statistics, and I'm going to have a look at time for comparison. I'm going to have a look at the square root of time, 1 on time, log 10, log base E, and then let's look at may as well stick all these arctans in, see what they come out with. Again, I'm really just interested in the skewness and kurtosis. You can chuck out the means if you want. Okay. So here I'm interested in getting a kurtosis as close as possible to 0. And you can see here all these arctan transformations, they're really quite severe. They've actually managed to make the kurtosis go in the other direction. And the same with the skewness, it's actually flipped that in the other direction. So here I can see the lowest one, and this is the one I've used in the video, is the 1 on time. So that had the lowest skewness, which I wasn't so worried about anyway, and the lowest kurtosis. I also put in the video a whole lot of histograms, so if you want to pack a whole lot together for the back page of a report, you could try just popping them all in here. Now it's going to try and tile them nicely, so if you pick an even number like 6 together, then it should, that's 3, 4, 5, let's do the first arctan. It should pop them out nicely in a grid. If you put 5 in there, then you'd have a blank space, which is a bit of wasted space. And let's bring that down to 12 and see if that fits in better. And you'll notice here that the descriptive stats are missing for arctan. It's gone off the bottom, so you may have to resize the font of that as well. So just from looking at these histograms, I'll make those larger. So this was our original one. We can see it was skewed out to the right and we had a problem with the kurtosis. That still looks skewed, that still looks a little bit skewed. And this kurtosis actually looks higher. That looks much more extreme. I'm looking at the difference between the highest point here and the lowest ones. And the one that looks the best is also the 1 on time. So even if you're just doing this by eye without spitting out the values for skewness and kurtosis, I would probably pick this one. So the next step is to use this in your general linear model and then see how that fixes things. So ANOVA, general linear model. I don't want to change any of the model. I want all of this to stay the same. I really just want to change the response from time to, where is it, 1 on time. And we still want, I don't really need the coefficients for the terms in this case, but I do want the analysis of variance table and the storage. I want to store these standardised residuals again so I can do some more tests on those if I want to. Okay. So what we can see here is that they're still not quite normal, but they're better than before. I'm pretty happy with this. We've got this clump of tightly packed observations here, and this is probably the lemonade doing that, and the orange, and that means that we've still got this peak over here, but it's not as extreme as it was before. We should have a new column now for standardised residuals, so rename that straight away. So this was the 1 on time residuals. If you don't rename it straight away, you'll forget what they're for. If we do a couple of histograms with the fits, and let's look at time residuals full model and the 1 on time residuals. It's a nasty little plot, isn't it? I'll do those separately. Time residuals. So that's what we started with. Histogram 1 on time residuals. Oh. So that's the improvement in the residuals. Now the general linear model, or analysis of variance, if you're doing it that way, is fairly robust to violations of assumptions. So I fixed this enough for me right now. I wouldn't take that too much further, mostly because if I look at the output, although I've still got these extreme observations or unusual observations, I can see that the model fit has gone up. And these p-values, everything is just about, that's gone up a little bit. These have gone right down. So the two hypotheses that were most at risk from the violated assumptions, so these were the ones where I was most worried that I would have a false reading, these have dropped right down. So I'm more confident now that all of these factors are significant, and I'm not going to chase a better transformation. And it's quite possible you will never get a perfect transformation. There's no guarantee that anything would work better than this, no matter how complicated it was. What might be sensible, if I was going to do some further research into the time that soft drink fizzed when you drop bicarb into it, in all seriousness, is I might split up the Coke products from the other products. If I go back to, I had a box plot somewhere. Box plot of time. If I go back to this one, you can see that there really is a difference between the Coke products and the other products. So what I might do if I was doing further investigation, or it's part of my conclusions, I might say it's possible there's something different that Coke does with its products which makes them more variable in the amount that they fizz, and so we might want to run a separate experiment for Coke versus non-Coke.